I'd like to welcome you to CSCS. Yes, I did put my name in there. My name is Jean Favre. I've been working here at CSCS for quite a few years. I'm a specialist of scientific visualization. Scientific visualization, I said, not information visualization. I can't do it all. What is information visualization? It's this activity that has to do with a lot of multidimensional data, but not strictly related to a physical space. As we know, X, Y, Z, and then physical quantities. It's all the big data from Google and etc. That's information visualization. Now we're going to talk about VTK and ParaView today. In VTK, there are actually quite a few things to do information visualization, but I couldn't claim to be an expert at information visualization. We're going to focus on scientific data visualization today. I've titled this course Advanced Visualization, and in the prerequisite I wrote that people should have at least a minimum experience with VTK and ParaView. Is that true for everybody? Yeah, you all claim to have a minimum. Very good, very good. Now, how many of you actually do parallel visualization? Just a few of you, okay. Why are you not doing parallel visualization? Is it because you don't know how to, or your data maybe is not yet big, that you don't have that requirement? It's a little bit of both, perhaps. Okay. Somebody here in the group doing big data. What's big data? That would be a good question to ask. Some years ago, a colleague of mine, Jim Ahrens from Lawrence Livermore in America. Jim is one of the actually leading person in the development of ParaView. I have met Jim, I forgot how many years ago now. This was ParaView version 0.9. You can imagine this is way back a few years. And Jim was saying, oh, big data is whatever doesn't fit on my laptop. So there. If you have a small laptop, if you have I don't know if it exists anymore, a laptop with 4 gigabytes, that would be too small today. But say if you have 4 gigabytes, well, okay, big data is 5 gigabytes, right? If you have a bigger laptop, mine has 16 gigabytes, well then 20 gigabyte would be big data. And then at this point, I probably should be using a remote connection to a server and use the memory on that server. And then if a single node of that server is not enough, then I'll partition the data, and then I'll really get a large pool of memory. So using Piz Daint here at CSCS means that a single node has 64 gigabytes of memory, so that's already pretty comfortable. The GPU itself has 16 gigabytes of memory, so the GPUs, as you should probably know here on Daint, are the Pascal GPU from NVIDIA. They're really nice GPUs. So we're going to be able to do quite a bit of visualization already in this remote fashion. So anything bigger really than what fits on your laptop would be considered big data. Now, of course, for the tutorial, I don't necessarily work with big data because it gets kind of heavy, and each of you should be able to do things on your laptop. And I've prepared some examples with things that fit comfortably on your laptop. So that's the first thing. So as a visualization specialist here, I support several applications. Another very famous scientific visualization application and user application is Visit. Visit is also made by a bunch developed by a bunch of people in the USA. And the teams, the development teams of ParaView and Visit, I mean, there are some overlaps. Of course, at the base of this is the VTK C++ library. So all these people developing and using the end user applications, they are extremely comfortable with the VTK toolkit itself. So I want to make sure people actually understand those, have more than just simple notions of VTK to be able to apply some of the advanced techniques we will see further. We'll concentrate on ParaView today. Now, ParaView is an end user application, which usually means point and click. Okay, lots of menus. But then, and lots of menus to do things interactively and to do things in kind of a spontaneous fashion. You load your data and you say, oh, what if? And you try a particular visualization filter. And that's not interesting. OK, you delete it, and then you try something else. And then you might be doing this, at least when you first discover your data, you might be doing this for half an hour or maybe a couple hours until you find a visualization that is meaningful. And then you quit, and then you're like, oh gosh, how do I redo what I've just been doing for the last 2 hours? I don't have a trace of it. That's if you don't know how to use the Python interface. So I'm going to talk a lot about Python today, because if we learn how to use Python correctly, Python will be able to give us a scriptable visualization, which we can do multiple things with the scriptable but scriptable story. We can reload an existing visualization. We can share an existing visualization with a colleague. So, as you know, my position here at CSCS is in the service group. We are here to help the users. Now, how do I help the users? You don't send me a copy of the data via email. If anything, you send me the path name to the data, but not the data. And what do I send you? I don't send you images or a movie. Well, maybe sometimes I do send images and a movie. But most of the time, I would say 98% of the time, we're going to trade Python scripts. Because you're going to ask me, for example, how do I implement a particular feature? And my answer will be not an image, it will be a script. And I'll say, here, you do this on your laptop. And that's why it's really so important, because this will be the way for us to replay something, share something, and then debug things. And then once all of this is done, using the same script, we'll run in batch mode, and we'll launch a movie generation, for example, on the supercomputer. Okay, so that's the preamble. I've asked you to download ParaView version 5.5. Unfortunately, the timing of this course is such that we are just a few days ahead of the official final release of 5.5. No problem with that. We have release candidate 3, which has been thoroughly tested already. I can tell you that when release candidate 1 came a few weeks ago here at CSCS, and my job is to test ahead of time to make sure things work fine. That release candidate didn't work. They had a big bug that had just been introduced before release time. So we corrected that. Release candidate 2 came out. We corrected more little problems. We are now on the 3rd iteration. I expect this to be 99.5% of what the final release is going to be. Okay. In fact, I do check on a daily basis with Git pull request what comes into the release, and now it's I mean, we've reached the plateau and we're just doing testing and then multi-platform builds, etc. So it's nearly the final release. If you like it after the class, in a couple of weeks when the final release will be available, you should simply wipe out RC3 and then install the official release. Now, why did I want to be so close to the leading edge? It's because I want to offer some of my expertise and experience with the NVIDIA Index plugin. This is a new development specialized for volume rendering, and we're going to spend, I hope, a lot of time doing volume rendering. This is a new development, so it's release candidate 3 is the first release where that material is included for all of you. For the desktop versions, I understand, free of license until there will be, I'm sure, official communications from NVIDIA on how end users should be using the library with the final release, okay? So Index is available on this release, which you should have installed on your laptop. It's also installed on Piz Daint, so we'll be able to do as well remote visualization using the Index plugin. Now, when I say remote visualization, what does it mean? It means that we will have a ParaView server running on a compute node of Piz Daint, and then there is some transfer between that remote server and your laptop. Do you all understand? Do you know what gets moved over between the client and the server? Is it your big data or is it something else?
It also depends on something.
Exactly. It depends on a threshold, actually. So, and we'll have to make sure we show you this particular threshold on the settings of the graphical user interface. Now, the typical scenario in large data visualization is that the data is very big, so we keep that close to the file system, close to the server. We execute the visualization algorithms, filtering, etc. And then the final result is we want an image. Well, an image is very few megabytes of data. Take a standard desktop, maybe 1024 pixel wide, or let's take HDTV 1280 by 720, multiply that by 4 bytes per pixel. This is very little. Maybe you have a terabyte of data that was processed, but the final image is HDTV resolution times 4 bytes. Maybe it's compressed, and that's what gets sent over to your laptop in the big data scenario. Now, if you're doing toy data sets, if you're doing just something very trivial, very simple, it might be advantageous to actually send not the pixels over to your laptop, but send the geometry generated. Why is that? If you are animating, with the standard rotation, zoom, scaling, etc. on your screen, if the object is very small, if it fits comfortably on your laptop, then once it's on your side, on your laptop, on the client side, then interactions should be super fast, and you're not going to use the bandwidth between your desk at the office, wherever you are, and CSCS. If you're doing a movie, for example, what would be a movie with a time-dependent data set? You would load a data set that would take a long time, perhaps a long time, process it, make one image, and then throw it all out, load the next time step, and so on. In that case, what's the point of sending over to your desktop something very heavy that you're not going to interact with? You only want to save it to disk. So in that case, you really should be doing image transfer. Those are some of the cases. That being said, I think I'll start showing you ParaView. Now, there are excellent resources on the web, user's guide, examples, etc. And I don't necessarily want to go through the tutorial that's on the wiki. What's the point? I mean, you can do this very comfortably at home, sitting in your living room, maybe with a beer or whatever is your favorite way of interaction. What I want to do today is things that perhaps don't show up in the user manual. You know, things that are a little bit off. I wouldn't say off topic, but things that are a little bit more advanced. That's exactly why I gave that title of Advanced Visualization to the class. All right, that said, the usernames, the user accounts I'm circulating here are for you to log in, and we'll use that for the client-server connection. The PDF for this session this morning is available on that directory on Daint, and then we'll go on with the motivations for this morning. So I didn't write the coffee break, but please do remind me that we should take a break. Otherwise, I'm capable of just talking until 5 o'clock tonight. We'll introduce ParaView and VTK, describe the pipeline, and here there's going to be some overlap with the things I've done 2 days ago, unfortunately, but we have kind of a mixed group. Some of you were here 2 days ago, some of you are new. I need to repeat those things and perhaps go even in more details. We'll talk about the pipeline and the VTK object, but I'll try really to concentrate on ParaView. So write ParaView pipeline should be the focus of our exercise today. And then exercise the Python programmable source and filter. And then after the coffee break, this is the coffee break right here, we'll focus on volume visualization. Do you all have a minimum experience with numpy arrays? I don't need to give you a tutorial on numpy, right? What's numpy? A Python library to deal with large arrays of contiguous numeric values. And that's also the focus of visualization. Usually you have large arrays of data. Now, VTK has its own internal structure to store those arrays of data, and I'm talking here about coordinates, scalar field, vector fields, and so on. And then NumPy has its own way of doing this, and the really neat things about ParaView is that now you can interchange those. You can use VTK arrays where NumPy arrays are required and vice versa. So there's a very smooth transition between the two. So we'll need a minimum really of NumPy knowledge. I have the NumPy book on my desk. I've never gone past the first 30 pages, okay? And then if I ever need one thing, I go to Google and I ask the question. So no need to be an expert there. However, one distinction I made already 2 days ago, the gradient of a scalar field will depend on the particular structure you have underneath the mesh you have. If you have a Cartesian grid that is also distributed, partitioned among parallel servers, you're going to need to have communication between the neighbor processors to do the correct gradient calculation. So in that case, VTK would do a better job of handling inter-process communication, of handling different mesh types, etc. So this would be the advantage. The standard pipeline, as I'm going to say a lot about the visualization pipeline is really this network of reading or receiving data from a source. Most often, in our case today, the source is going to be the disk. But for the last couple of days, we've talked about in situ visualization, where the data can come from a running simulation running on a second resource, for example. And then we'll do all kinds of filtering here as the intermediate path through the pipeline, and then we'll do rendering. So rendering means making images and so forth. So I'm going to try to maybe accelerate through some of those early slides because we've seen them already a couple of days ago. But if you have questions, please, please, please stop me, and then we'll give more details. The execution path is both event-driven and domain-driven in ParaView, and we'll have to understand really what does that mean. But basically, you read data, you apply immediately as you build the pipeline, you apply, you click on the apply button, and that actually forces the execution of your pipeline. Something we have to understand, and I have an example that is going to demonstrate that too. I'll have to make it available to you. ParaView uses a multi-pass execution, let's say, engine. Once you have a pipeline that you are defining, at the beginning of this pipeline creation, there's some lightweight data, metadata, that is being exchanged in order to build up the visualization. So this is really the source of data, the reader of the data, advertising, the type, the number of scale of field, the number of time steps that are available in the simulation output, such that the pipeline can be more effectively set up. And then this idea of the sink is actually a really good name. The sink is something that's going to pull the data the end of the pipeline. So depending on what we expect for the output, the final output, the sink, there's going to be a certain number of requests traveling up this pipeline. This is the metaphor of the event-driven execution, to make sure that whatever will get executed in the pipeline is of the right form and shape, etc. Here's an example. What would, in the ParaView pipeline, what would come up this pipeline in what we call the update region? Well, the value of the time step, for example. If I am using a time-dependent, if I have a time-dependent output stored on disk, unless, or I should say, except for some very particular cases in ParaView, normally I always have only a single time step. So if I am at time step 10 and I want to go to time step 11, that information is the information that travels up the pipeline all the way to the source, and then the source says, you are asking me for a new time step, it's time to re-execute. Okay, I think that's a simple example of the type of information that comes up, which actually here I'm giving you some fundamental information already. It's exactly how you will animate a Python script. Setting up the time step will come from the bottom of the pipeline, will come from the viewer. In ParaView, the viewer owns the information about the time step. We'll have to remember that. Finally, when the visualization pipeline is fully described, the pipeline can execute, so there is a data flow, if you want, from the source through the filters down to the sink. The sink would be making an image, for example. Now, this is an iterative thing. You can pull filters out. You can delete filters out of this pipeline. You can add more pipelines, etc. And every time you modify that pipeline, I want really to teach you during this seminar today to be aware of what's going to happen in your pipeline. Let me give you an example. This would be from the very first page here. I read some data, I do an ISO surface, and I make an image. And then the shading, the colors on the surface don't look quite right. I can actually see the details of all the little triangles on my surface. Have you all seen that, more or less, if you use low resolution data? It's because the shading, the illumination equation that is used, uses an approximation. For each little triangle, there is a unique direction for this triangle in the polygonal mesh, and the shading is uniform. So there's one filter that we can use in ParaView called Generate Surface Normals. It will calculate exactly the direction of those triangles and then average the surface normals at each vertex of the polygonal mesh, and then you will get a better illumination on your surface because there is a smoother interpolation of that surface normal. Well, to do this, ParaView, under the hood, transparently, this is why it's important to understand, because it's transparent. ParaView computes a gradient to do a smooth interpolation. Well, what is the implication of that? To compute a gradient, if you're on a single task, single processor, no problem. If you are in a distributed fashion, you need ghost cells to do the correct grading calculation. What does that mean? That as you insert here a generate surface normal filter, you might not get an immediate image. Why? It's because the full pipeline is re-executing. Because if initially the reader was not aware or was not capable of providing ghost cells, it says now, oh, I have some new requests now. I need to generate ghost cells, so I need to do some data processing here. All right? So this is going to be transparent, but it can have some big impact on your visualization pipeline, mostly because the reader here will be responsible for generating data at a higher resolution, including the ghost cells.
But in this case, does it mean that it also depends on the file format, because the reader will depend on what file format you use?
Of course.
Not all readers can handle the request from all filters.
Of course, of course. It will depend heavily on the data format. So some smart readers, for example, can anticipate this and immediately on their first request say, hey, I'm going to generate ghost cells anyway, because I'm pretty sure you're going to need them in the future. All right? When we talk about volume rendering later on, to do correct illumination, again, we're going to need gradients, and again, we're going to need ghost cells. So some readers are not capable. That's just legacy file formats. They're not capable of generating ghost cells. for those, we're out of luck. There are other data types that we should talk about. If you're doing SPH, particles only, what's a ghost cell? There's not really the notion of ghost cells, but you can have the notion of particles close to you on the next processor. This would be useful if you're doing, for example, an SPH interpolation on a plane. If that plane goes across processor boundaries, you'll want contributions from the other particles. So the notion of neighbors, I guess, is more correct than just strictly ghost cells, because if you have particles or atoms in a large molecule, you'll have to know what your neighbors have. So the calculation of gradients here would force the re-execution of this pipeline. Okay? How would this work? I add a generate surface normal here. The update region, which means the request for partitions plus ghost cells, that's an information, needs to travel back to the source, and then the source can finally re-execute. Now, some fields, when we run in parallel, this pipeline will be instantiated multiple times for the different MPI tasks we have in our ParaView server. Again, here, the generation of ghost cells, for example, is an example where we will have communications between the parallel filters. Otherwise, if you do some simpler visualization, those pipelines can run independently, at least until the end, which is the compositing of the image on the screen. All right, so basically the pipeline is data sources, filters, mappers. Usually we don't see the mappers in the visual representation of the pipeline in the graphical user interface. We see, yes, we do here, exactly. We see the data source, the filters, for example, a contour, which is an isosurface filter, other filters deriving from it, but you don't actually see the notion of the mapper. It's implicit. ParaView creates a mapper, and that's the Python command we will learn. It's called show. It's pretty simple. You give it a name, and it creates the mapper for that particular entity. And in the rendering. If you've opened ParaView before, you know that there are a lot of sources here, quite a lot of filters. You can have different categories of filters, and that's, those are examples of your pipeline. Now, I've said that this is really a bidirectional exchange of data, some lightweight information traveling first to establish the pipeline, then request for updates, and then finally the heavy-duty computation takes place. In a typical VTK Python syntax, this would be the objects that you instantiate, a render window, and then you actually trigger the execution of your pipeline with the command render window render. Using the ParaView syntax, it will be simpler. I will only have to type render like this, and my pipeline will execute. So I've prepared some examples, which are those examples are really for VTK Python. VTK Python, unfortunately, uses a different syntax that the Python Python used for the management of the pipeline in ParaView. So I think I'm going to leave those slides here, therefore your knowledge, and we'll concentrate on the ParaView syntax itself. But this is interesting. It's in more details the equivalent of what ParaView would do. So always a source of data, a filter operation, a mapper operation, and then anything that has to do with the rendering itself. All right. VTK as a C++ toolkit is a large collection of hierarchical classes, which are basically of two types. The VTK data objects here, it's one class hierarchy with all the different mesh types that are typical in scientific data visualization. So the structured mesh, the unstructured mesh, the point meshes, molecule now, which is really a graph. A molecule is a connection between different atoms connected by bonds. So it's really a graph. And then you have the algorithms where all the filters are embedded in this category. Here we have an example of, for example, a geometry filter which derives from VTK polydata algorithm. We have to be aware of that distinction between the different mesh types. VTK image data is one mesh type, the Cartesian grid in ParaView. The rectilinear grid is another type. The structured grid is a grid where we specify explicitly all coordinates. The unstructured grid is where we specify explicitly the connectivity between cells. And then you have the perhaps less traditional mesh types, graphs, molecules, etc. So depending on the type of data you have, and polydata is really similar to unstructured in the sense that polydata is a collection of triangles, quadrilaterals, points, triangle strips, etc. It's closer to the rendering. All right, so now a little bit of numpy just to wake up well, mostly me. I hope you had a good night's sleep. Here, the definition of a Cartesian grid, that's VTK image data. It has a set of coordinates, and there are three, which means that by default, there's always three coordinates in VTK because we assume spatial coordinates x, y, z. There's a special case I will show you later in an exercise I did last night at home to prepare the slides, the so-called texture coordinates. If you want to apply a texture in graphics, what does it mean? Take a photograph or an image and then map it onto a polygonal surface. Now, the trivial case would be a flat, two-dimensional plane in space, and you map an image of it. It can be the image of the photograph of your dog, or it can be a satellite image, or it can be anything. And for this mapping, an image is two-dimensional. We only need two coordinates for the mapping. So that would be kind of the difference. But usually it's 3D, so we need to have x, y, and z coordinates for the description of the data. The Cartesian grid is implicitly a grid with regular spacing everywhere. So we only need in that case to define the spacing and the origin of the block. And yes, even if you have only 2D data, you still need to provide a z coordinate. In that case, it can be 0 or it can be any number. If you reset the camera on your image, you'll see the data. But beginners often make the mistake to assume that, hey, I have 2D data, I just specify x, y, and it doesn't work. You must specify a z coordinate. Same thing for 1D. If you have 1D, you have to specify an epsilon and z coordinates of 0. In that case, and this is what I like about the numpy interface, there are some simple commands, for example, point data or cell data, those dictionaries that you associate with a grid object, they give you direct access to plug in a numpy array of data. Do you have a question?
Yes. So I have, I think, notion of 3 dimensions where there is the beam which set at the voxel side or the resolution of the volume data, and we have the axis which define the real world mean and mass, and then we have spacing. What is the spacing?
So the spacing is the spacing between grid points. So it's really the width of the cell. Some people talk about voxel. I think I heard you said the word voxel. Voxel is usually said when we talk about medical imaging, for example. We talk about voxel. If you talk about more, I don't want to say more scientific, but other types of grid, the hexahedra would be a voxel. Would be very similar to the voxel. The voxel is basically a small cube with 8 vertices. Okay? In the case of a Cartesian grid, we only specify once the spacing everywhere here along the x direction, everywhere along the y direction, everywhere along the z direction. So this doesn't mean that those 3 numbers have to be equal. They can be different. But it's going to be a fixed increment along the x direction and a fixed increment along the y direction and so forth. This would be the canonical example, origin at 0, spacing of 1, and then the dimension of your grid.
But they have to be consistent when you set them in the x-axis on the axis.
No, I think there were, yeah, there's actually some colors here in my graph. This is really all you require to define the grid. Here, I mean, perhaps this is confusing. I'm declaring again a set of x, y, z axis. It's only as a support to create some synthetic data. Okay, it's just a numpy trick. But to define if my data array, if I were to read my data array from disk, for example, this is the only thing I would require. And the last command, which is take my data array, my numpy array, wherever it comes from, and connect it, add it to the point data dictionary. So don't be confused with those 3 definitions which I use just as a support to generate synthetic data in this case. If we're reading data from disk, I do a lot of H5 for example, to read data from HDF5 from files stored in HDF5 format. Those would be the 5 lines required, and H5 pi, and I get confused, an H5 pi command would read my data from disk, and then that numpy array I would stick in, for as many scalar fields as I have, I would add to the image grid. All right. Running in parallel, that pipeline is going to be duplicated, as I said. And what is important to understand is really that the large data will be divided if possible. Now, oftentimes, I would say on a regular basis, I have people come to me and say, oh, I'm using multiple servers, n servers in parallel, and the visualization is so slow, it makes no difference. Why is that? It's because the data format they use, and we said that already 15 minutes ago, the data reader does not know how to divide the data. And it's a very common error. And I'm not blaming anyone here. It comes with experience. You have to understand the file format you are using, and you have to make sure it's reading data in parallel. Otherwise, it's no use to throw in 1,000 processors and node. How do we check that? Very simple. ParaView has a filter called process ID scalars. You can simply color your visualization with the color of the processor, and that would be a quick hint. Aha, I only see blue. Blue means 0 usually. It's only processor 0 doing all the work. All the others are sitting completely idle. So what does it mean? People keep adding servers and memory to it, and there's a single processor consuming all the memory, and it crashes. And they say, I don't understand. I have 64 gigabytes times n servers. There should be plenty of space, and it crashes. Why is that? Because they're using a format that is not adequate. And this is where I've got lots of experience going through those cases, and this is where I can help you. All right. So Python, the Python programmable source. All right. So ParaView has a lot of file format readers available, probably 100 and more, if not 200 and more. How do you choose one? This would be a discussion to have with me and other visualization experts before saying, oh, just because my colleague next door, he uses that format, it's probably good for me as well. No, please, don't. Anticipate. Say, I'm planning to have some large resolution data. It's going to be seismic data, for example, a large reservoir of dimension 8,000 cube. What would be the best way to store it to guarantee that I can run it in parallel? So the discussion to have with me would be, okay, do you know file formats that would fit that particular requirement? I might be able to suggest an existing format, and this is what I would prefer because it would mean I don't have to do the work of developing a special plugin. Of course, there's always legacy problems and requirements that are specific to a project where you have to implement your own reader. And in that case, the ParaView programmable source would be your lifesaver because it would allow you to prototype very simply with Python a reader. And then once you have it working well, then you could always, I could collaborate with you on making that plugin a C++ plugin for efficiency. So the types. So the first thing to do in a Python programmable source would be to define the data set type, and we'll have the choice between polydata, structured grid, rectilinear grid, multi-block, etc., AMR, tables, and that would be depending on your data. Yes?
But this programmable source is able to automatically work in parallel as well, or has to do some tricks there?
Yes. It is. It's the first line of the slide here. In client-server mode, the script is going to be executed on the server side, which means in parallel. If the server is parallel, it will run in parallel. Now, by default, it's going to be dumb. It's going to do exactly the same thing for all, assuming the full volume. And I thought I wouldn't talk about it immediately, but there is one line that you should have in your Python script to say, don't replicate the full pipeline using the full dimension on, because that's also something that I see if people use a data reader that is not adequate. Every processor is going to read everything. That's also not the solution. We want every parallel server to read 1/n of the data partition. And this would be the key to the programming. Perhaps I'll jump quite a bit ahead to show you a picture. There we go. Picture I made this morning at my desk. There is a sphere that is distributed in parallel, and the coloring I was mentioning earlier to make you debug, to make you confirm that you have a parallel running server. This would be processor 0, processor 1, processor 2, 3, and then in the back you can see. So what happened, the spherical shell was intelligently subdivided into equal parts. And then what matters is that the visualization actually is done appropriately. So we'll go through this example later. But this is the case where we know the global dimensions of the grid, and then each server says, I'm only taking from the equator here to the North Pole, and I did this with 8, so this would be 90 degrees from the meridian, 90 degrees east, and another 90 degrees for another processor, and so forth. Where am I? There we go. All right, so the grid types, we've talked about them. The image data, which has regular spacing. The rectilinear data, which has, in this case, an explicit list of 3 arrays, 3 one-dimensional arrays, which give you the x coordinate in one direction, the y coordinates in the second direction, and then the z coordinates in the third dimension. And in that case, you explicitly give the x coordinate array and the y and the z. And then finally, what I often call curvilinear grid. So often people ask me, I have a cylindrical grid, I have a spherical grid. How is this implemented in VTK? The answer is it doesn't exist as a native data type. VTK does not have a VTK spherical grid object. It does not have a VTK cylindrical grid. But that is a cylindrical grid. It's just a special case of structured grid. If you take this and warp it in space, then it becomes completely structured but arbitrary in space. If it's flat, that's what I call a cylindrical grid. It's in 2D in this case because I gave it the z dimension here to be 1. So all of you people doing geophysics problem, climate, and what other types of the typical people doing computation in spherical space and etc. We can implement that very well in ParaView. I've worked a lot with the geophysics department at ETH Zurich. They do computation in Fourier space, so in R, theta, phi space, and then FFTs, etc., etc. I read the data in the native space, R, theta, and phi, and then I build up the coordinates using the simple trigonometry equations to make up that grid and to make it be spherical. Unstructured grid. How many of you, just for curiosity, how many of you do unstructured meshes here? One person. You? Meshes of what type of elements?
Just
triangles. Triangle. Oh, so in 2D topological space. Okay, okay. And you?
Three-dimensional hexahedra or tetrahedra.
Okay, okay, very good. So you said hexahedra or tetrahedra. There are multiple cell types in unstructured meshes. We can have mixed types, okay? There's absolutely no limitation. You can have a few being from 0 to millions, tetrahedra, a few hexahedra, etc., etc., all in the same mesh. Here, those are examples where I only have tetrahedral cells. Which brings me to a consideration that is very important and that is often underestimated. Even though you read data in a structured grid, as a structured grid, so very efficient in memory, you also have to be aware that some filters are going to change the type of your grid. And it might explode in terms of memory cost. I'll give you an example. Working still with the same people, or was it? No, it was a different type of people doing planets. So spherical objects by nature, but they're using volumetric Cartesian grids. And the planet itself, the sphere itself, is embedded into that volume. And we read the data as a 3D Cartesian object. And then to extract, this was the case of Jupiter. I worked a lot with that particular planet. To extract the surface of the sphere, I would extract using a particular threshold. Now, if I only want to extract the shell, the outer surface of the planet, it doesn't cost very much. Maybe a few million polygons. That's nothing. But if I want the 3D cells within the globe, embedded in this 3D, into this 3D Cartesian grid, I have to use a threshold filter. So, good, you go to your GUI, threshold, on this particular, the thing blows away, bam! Because from a grid of 2,000 cube in memory, it becomes a mesh of 1 billion elements. And because of unstructured grids have the need for an explicit list of coordinates and connectivity and cell types and cell offsets, bam, you explode. So when you do your work with big data, the message is always take a deep breath before clicking apply. I mean, think about what's going to happen. What I'm saying here is very well documented. There's one page in the user guide. I think it's about midway through the user guide. It gives the list of all the filters that actually change the type of your data and then that have a large impact on the memory consumption of your visualization. So, in fact, I could just quit now for a second. And I forgot, how do I get out of my, there we go, here's ParaView. So this is back to my Linux desktop. I'm going to start ParaView, and this would be the first blank page. I'll generate a data, and at the bottom, the very bottom of the source, there is the wavelet object, which everybody uses for benchmarks and so forth. I'll give it a dimension of 201 cube, because here I'm using minus 100 and plus 100 in all directions, and that is the first thing we need to, there's a cube. Information, the information tab about this grid shows effectively that we have 201 cube, and it has one scalar field, and it gives the minimum and maximum of that scalar field. And it gives a nice bounding box, so this is very lightweight and doesn't show very much. As soon as I go to the surface representation, even though nothing happens in your pipeline here, we had to still extract this surface. So some processing took place, and then the scalar field is available on that surface, and we can color it. It's kind of a sinusoidal shape object in 3D space. So this is why we have those wavy patterns on the data. Now, if we don't like the colors, we can of course always go to a more colorful data set. I think this looks better on the screen anyway. Now, the information tabs tells us everything about the data, and it tells us exactly that this is a uniform rectilinear grid. Now, if I'm going to do an isosurface contour at a particular threshold, and then by default, ParaView is going to take the midpoint in the scalar range. Here, I'll say apply. There is the isosurface of that particular field. And guess what? The type has changed. We now have a polygonal object. Okay? So good. We've gone from a rectilinear grid to a polygonal object. That's the first thing. There's no colors available, but there is already a normals, a scalar field called normals that has 3 components, which is really the estimation of the surface normal. So that means some gradient calculation took place. Well, this is a single processor. Actually, no ghosters were required for this specific case. Good. I'll hide this for the moment, and I'll go back to my mesh. If I do the same thresholding now, using the scalar, I should have done the invert. Okay, it looks the same as before, right? What's the type of it? It's now an unstructured grid, and it has 4,822 something cells. So we've gone from a rectilinear grid of 201 cube, and we've transformed it into an unstructured, which actually weighs a lot more in memory, an unstructured grid. All right, so this is an illustration of what I said, that in your pipeline, there might be explosion in memory because as you apply things in 3D. Now, what's the difference of this between this and the previous contour? which is here. I'm going to make two windows, render here. You'll see how convenient this is. Here's the ISO surface. I'm going to link this camera with the other one so they are moving together. In this particular view, I have the volumetric on the left, the volumetric object. Here I have the outside shell of the same object. Now, I would have different purposes for that. Here I can compute the volume of that object. Here there is no volume, it's empty. As you can actually see here through the holes, I can see the background color, the white. So it's an empty thing. Here I can calculate the surface, but not the volume. So depending on your data analysis requirement, you have to use one or the other. Okay, now I want to look at one last thing. The ISO contour weighs 29 megabytes in memory, and the clip is 420 megabytes, so it's 10 times as big in memory. There, I think I've made the point. It's not, as you allocate resources for your visualization, you should not only think, okay, I have a grid 1000 cube, 4 bytes per float. It's going to take exactly 4 megabytes of memory on my machine, and I'm done. I can run on one node, easy. No, it's not. As you build up your visualization pipeline, the requirement in memory is going to grow. Okay. Now, time-dependent data, ParaView doesn't load time-dependent data, doesn't load all time steps at once, except in one particular case. So the requirements are really just one time step, the memory required for one time step. Okay, very good. Any questions here? Now, I've talked a lot about Python. If I quit this, then I lose everything. What's the way to do it? I go to File, Save State, and I have two options. I can save a ParaView state, a so-called ParaView state file, or I can save a Python state file. Now, I'll say it as a joke. If you expect me to help you, don't send me a state file. Send me a Python script. I love Python script. I hate state files. I never use them. It's perhaps the only thing negative I will say about ParaView. I much prefer Python script because they're readable. They're human readable. The state file is a complicated collection of objects. Have you ever looked at a state file? It's really difficult. So in many cases, the state file actually works well to reload a visualization or to share with a colleague. But you cannot hope to take a smaller piece of the state file, use it in another visualization scenario. This would be impossible. Okay, so use the Python script here, and I'll just give a standard name, foo.python. I'll save, and now we're going to inspect that file. Perhaps I'm going to try to make a big font for you to look at. Where did that thing get saved? Let me preferences, fonts. Let's try this. Can you all see that comfortably? All right, because we're going to study this for a bit. All right, typical Python command, import the module. So from ParaView simple, it's called simple because the syntax is pretty simple, import all. And at that point, I'm good. I have all the ParaView available under my hand. Create view would be making the 3D window for interactive rendering, okay? And you give it a type name. So by default, the render view is the 3-dimensional typical rendering view. You can specify a particular resolution for the image, view size. The rest is a little bit, some details we don't need to worry so much about for the moment. Yeah. Then we had 2 views in that particular visualization. So the next command is another create view command. And it has a different name, okay? Now this is called render view 2. The previous one was called render view 1. Very good. We're good with that. It has also a specific resolution and so forth. Now the data. Wavelet, that's the data we generated. It's exactly the same name as we had on the graphical user interface. It's called wavelet. Instead of using the default parameters, I specifically said -100, +100, etc. So here, you prototype it at low resolution, then you change one line and you do a big visualization, okay? There, the contour is the isosurface. So here, I gave it the standard value, the default value was the mid-range value, so 160. So we could change that to be exactly 160.0 there, a nice clean number. The second object is the clip. This was the volumetric clipping of the mesh. And I have, here I'll change again to 0.0, and I'm done with that. And then I have the command I've already mentioned earlier, show. Show is the bottom of the pipeline. It's making the graphical object, making the mapper for it. And the object we get called display, that object has all the parameters that are typical of graphical objects. So the representation type, for example, surface, the color, the name of the array by which we are coloring, and so forth, etc. More glue. Here's the second show command. And that's it. So that's my file. And now I'm going to read it again. I run ParaView. I go to my Python shell, which is here conveniently. I've pulled this, I've docked that panel here to be conveniently placed. I do run script, and I say foo.py. And it doesn't quite work. The layout is not quite right, and it's actually a good illustration. The ParaView state is not 100% of what you had on the screen. It takes a little bit of tuning. So here, so this would be also where I can contribute a lot to helping you, is in customizing really the Python script to make it fit exactly. So here, the problem is that ParaView by default creates a new window. So if I delete that unused, that default window, I'm back to my 2 windows. But things have been disconnected. See now, this one is independent again of this other one. I can reconnect them again by saying link camera. You click on one, and then you click on the second one. Now they're connected again. So the only thing that I would have to fix now is make the layout vertical. It's a couple of lines of Python, which would be the way to contribute. Now, if I go to my contour interface, and if I go to the properties, we see here that we have exactly the value 160, which I had put in my script. There. So I'm basically done. Now, I'll quit this. I'll edit the file again. And I'm going to show you the minimum well, that's quite a lot of stuff already. Oh, here. How many lines of code do you think is the shortest possible pipeline I can write? Take a guess. 10 lines, 20. Here I just deleted 3 lines already. 1 line. The answer is 3. 3 lines, I'll get you a visualization on the screen. Look, I've just imported the ParaView simple module. I can say sphere, show, render. I'll save this as my file, and I'll run ParaView script equals foo.py, and I have a sphere on the screen here. Of course, I have no data, I have little attached to it, but that's the minimum. So this is the lesson I want to pass before the coffee break. Yeah, we're good. It doesn't have to be complicated. With those macros, you can do a lot with little Python. Okay, that example also you'll find in the user's guide. Sphere, show, and render, 3 lines. The amazing thing is that this is also going to run in parallel. I will demonstrate that. To go parallel, I go to my settings, and I go to the advanced. By the way, there's a little wheel here that you can turn on or off to show all the advanced parameters in the graphical user interface. And I'm going to use enable auto MPI with 8 tasks, apply, OK, quit. I'll run it again and watch my screen if you can. Let me make it bigger. OK. Here, MPI exec, that was pretty fast. MPI exec minus n, 8. And I have the same visualization on the screen, and it's running on with 8 servers. I need 2 hands. That's 8. There. How does it show that it's using 8 processors? I can't see any difference. When you run in parallel, automatically you have this scalar field called VTK process ID. I just have to color by the VTK process ID. And sure enough, I have my little globe here that was distributed around 8 processors. Now, it's very low resolution, right? Look at the surface with edges. OK, now if I want to do a full Earth, I would use a minimum of 360 resolution here. Yeah, and then a minimum of 180 degrees of latitude. There, I have a nice little ball, really smooth. That's my Earth, or Jupiter, or your favorite. Okay, cool. I didn't have to change the Python script. The same Python script worked in parallel, and it worked on 8, so I prototype it on my desktop, then that Python script I copy to Daint, and I say run with whatever allocations you have, and automatically 99% of the time it will work, and then the 1% I will contribute to help you make it happen. Okay, there's often a little bit of tuning to do. Oh, and by the way, I have 8 pipelines here. So 8 pipelines, 8 images, and then they are composed together. This is a very advanced topic. It works. That's all I have to say. It works. Okay.
ParaView uses a sort left algorithm?
ParaView can use a different number of compositing algorithm. If the geometry is opaque, what does that mean, opaque? It means the opposite of transparent. It's very simple to take 2 images. No, let's look at, if you follow my mouse pointer here, that particular pixel on processor 0 is in front of me. So the distance between my eyes, the camera, and the blue pixel is this. On the back, there's processor 7 that has the same pixel, but it's further out. So ParaView knows the distance for each pixel, knows the distance between the camera and the pixel. And if the geometries are opaque, it's very simple. Take the closest one wins. So I throw away processor 7, which was over here. I keep the blue pixel. That's it. When things are transparent, it becomes more complicated. Furthermore, if things are on a tile display, you have to use another type of compositing. So for what we are concerned with today, the compositing here is sort last, and it just works as advertised. Now, I just changed you recall that I changed the resolution to be 360 degrees of longitude, 180 degrees of latitude. I'm going to save that script again. I'm not afraid of overwriting the file, so I'm going to say save foo.py always, yes. I exit, I quit. I look at my, so ParaView saved a bunch more things, but there it is. Sphere, theta resolution 360, file resolution 180. So that was just 2 more lines if I want in my ideal world. And I guess that's it. So look, I'll delete everything again except the ParaView simple import. I'll show just like before, and I can take shortcuts. I can say show. I'll delete everything again because those details are they're good default, but nothing else. I save my file and I run it again. MPI exec 8. There's my sphere. There are my processors. The resolution here is right. Okay? So I'm good. Last exercise before the 10:30 coffee, which we've missed already by a few minutes. Delete, get a blank page, get a sphere. There. Here's my GUI. 8. So the default resolution is 8 and 8, and I'm here with surface with edges. Okay. Can I directly type Python code in there? That would be nice. Yes, I can. I go to my Python shell. So that's another panel that you can dock here at the place you prefer. As soon as I clicked in the window, it executes from ParaView.simple import star. So I'm good with that. What is the name of my object? So ParaView has the concept of the active source, the active view, and then the active representation. So whichever of the object is highlighted in the pipeline over here. Well, we have a single object here, so there's a single active source. That's it already. So I just say S equals get active. And with the tab button, I don't have to remember this by heart. It gives me the choices. I know I want active source. So I select active source. I close the parenthesis. And I have S. S is the descriptor to my object. What can S do? That object. S can do everything you see on the graphical user interface panel. So for example, s.theta tab resolution 8. I change that to 360. Yeah, nothing happened. What did I do wrong? Come on, if you want coffee, you have to answer that question. You have to render. Very good. Okay, we can have coffee. Render. There. We're done. One more thing. You still have to earn the croissant. S. File resolution. File resolution is 8. I'm going to change it to 180. Nothing happens. If I take my mouse and I click on the window, automatically it forces the render. There, I'm done. So I saved myself another shortcut. And I go back to Surface, and I go back to Processor ID, and I've got my 8 colors I'm running in parallel. Life is wonderful. All right, let's go to coffee. Thank you.